Comparison of the natural growth and logistic models. In the 1930s, the biologist G. F. Gauss conducted an experiment with the protozoan Paramecium and used a logistic equation to model his data. The table gives his daily count of the population of protozoa. He estimated the initial relative growth rate to be 0.7944 and the carrying capacity to be 64. T days 0, 1, 2, 3, 4, all the way to 16, and then big P observed 2, 3, 22, 16, and it continues. Example 3. Find the exponential and logistic models for Gauss's data. Compare the predicted values with the observed values and comment on the fit. Solution. Given the relative growth rate k equals 0.7944 and the initial population p sub naught equals 2, the exponential model is big P of t equals big P sub naught times e to the power kt equals 2 e to the power 0.7944 t. Gauss used the same value of k for his logistic model. This is reasonable because big P sub naught equals 2 is small compared with the carrying capacity, open, big M equals 64, close. The equation 1 over big P sub naught times d big P over dt, where t equals 0, equals k open 1 minus 2 over 64, close, is approximately k. Shows that the value of k for the logistic model is very close to the value for the exponential model. Then the solution of the logistic equation in equation 7 gives big P of t equals big M over 1 plus big A times e to the power negative kt equals 64 over 1 plus big A times e to the power negative 0.7944 to the power, t at the end of the exponent, where big A equals big M minus big P sub naught over big P sub naught equals 64 minus 2 over 2 equals 31. So big P of t equals 64 over 1 plus 31 e to the power negative 0.7944 t. We use these equations to calculate the predicted values rounded to the nearest integer and compare them in the following table. T days, big P observed, big P logistic model, big P exponential model. We notice from the table and from the graph in figure 4 that for the first 3 or 4 days, the exponential model gives results comparable to those of the more sophisticated logistic model. For t greater than or equal to 5, however, the exponential model is hopelessly inaccurate but the logistic model fits the observations reasonably well. See Figure 4. The exponential and logistic models for the paramecium data. Many countries that formerly experienced exponential growth are now finding that their rates of population growth are declining, and the logistic model provides a better model. The table in the margin shows mid-year values of big P of t, the population of Belgium, in thousands at time t from 1980 to 2012. Figure 5 shows these data points together with a shifted logistic function obtained from a calculator with the ability to fit a logistic function to these points by regression. We see that the logistic model provides a very good fit. So we have t and big P of t. In Figure 5, the logistic model for the population of Belgium. Where big P equals 9800 plus 647 over 1 plus 21.65 e to the power negative 0.2 open t minus 1980 close. Other models for population growth. The law of natural growth and the logistic differential equation are not the only equations that have been proposed to model population growth. In exercise 22, we look at the Gompertz growth function, and in exercises 23 and 24, we investigate seasonal growth models. Two of the other models are modifications of the logistic model. The differential equation, d big P over dt equals k times big P open 1 minus big P over big M close minus c, has been used to model populations that are subject to harvesting of one sort or another. Think of population of fish being caught at a constant rate. This equation is explored in exercises 19 and 20. For some species, there is a minimum population level M, below which the species tends to become extinct. Adults may not be able to find suitable mates. Such populations have been modeled by the differential equation d big P over dt equals k big P open 1 minus big P over big M close open 1 minus M over big P close, where the extra factor 1 minus M over big P takes into account the consequences of a sparse population. See exercise 21.